So good morning, good afternoon, good evening, good night. So thank you very much for joining us today for another CASS talk. So today we have the pleasure to have here Professor Hao Cai from Southeast University in Nanjing, China. And also thank you very much for accepting our invitation to give this talk. And also thank you very much to Professor Rafael Brum, my colleague here in the Federal University of Rio Grande do Sul, that will be the session chair today. So, but today we are here to attend the talk by Professor Hao Cai, and in a very interesting topic. And the session chair will be Rafael Brum. So thank you again to Hao Cai and to Rafael Brum to accept our invitation. And I give the floor to Rafael to do the introduction of Professor Hao Cai.
So thank you, Ricardo. So Hao Cai received his Ph.D. from TELECOM Paristech, Universite Paris-Saclay in France in 2013. From 2012 to 2015, he was involved in the European EUREKA Program Catrene-RELY for high reliability nanoscale integrated circuits and systems. He worked with the Department of Communications and Electronics in TELECOM Paristech as a research associate from 2013 as as invited associate professor from 2018. From February 2018, he came back to China and he's now an associate professor with the National ASIC System Engineering Center in the Southeast University in Nanjing, China. He's author of more than 70 papers in numerous conferences and journals, and his research interests include memory design, emerging computing, and ultra-low power emerging device circuit interaction design. So, Hao Cai, thanks for being with us today, even though it's quite late in China, and the floor is yours.
Okay, so can you hear me? Okay.
Yes.
Okay.
I can hear you fine. Let me put your presentation back. And
okay.
There you are.
Okay, we get started. So my name is Hao Cai, and thanks for the introduction. So I'm from the National ASIC System Engineering Research Center in Southeast University in Nanjing. We just very nearby Shanghai, and we are the university with 120 years. So we can see the building in the left button. So it's almost 100 years ago. So my topic today is energy efficient In-MRAM computing. So the outline includes the introduction, the emerging, the NVMs, the non-volatile memories, about the state of the art. And the third part is the In-MRAM computing. I will show the recent work of the published work, and also my recent work and the ongoing work. So, and the first part will be the highlight of the EnergyAware Spintronics. And finally, I will give the conclusion and the perspective of the In-MRAM computing. So about me, I got my master degree in Lund University and the Ph.D. in Telecom Paristech. And now I'm with the faculty of the Southeast University in Nanjing. I'm also the invited professor at TELECOM Paris in France, and I serve as the technical committee at IEEE CASS. The subcommittee is Nano and Giga Scale Systems, which coordinated by Professor Marvin Chang. And until now, I'm the project coordinators with the speculative MRAM, the FDSRI, the energy efficient DRAM, and I also participate the STT-MRAM, the project, the EUREKA Catrene-RELY, the ST-Nano 2017, the SOBER, and with TELECOM Paristech. So along with the research lines, you can see I'm from the 146, the Rue Barreau in Paris, and now I'm in the 2 Sipilo, the Nanjing, China. So finally, I hope I can visit the Avenue de la Veuve in the Palaiseau. It's in the south of the Paris, because my the telecom, it has moved to the sud of to the south of Paris. So about the Southeastern University, so in short, it's SEU. So it's a research university with a comprehensive with engineering as focus. So we have the research domains like the architectures, the electronic, and the electrical engineering, information science, the basic science, and also life science and the social science. And we can see that we have almost 30,000 students in the campus and 3,000 professors and the faculty members in the different research domains. Okay, so about my research group, we normally we call it the ASIC Center. It's a National ASIC System Engineering Research Center in China. So we have the three departments. It's the first one is the SoC system chip. So they focus on the scenario about like the security, the 5G, the AI, the high performance computing, the Internet of Things, and also the circuits like the chip design. So they are doing the tape out. Like the on-chip memories, the SRAM, MRAM, DRAM, and we like me, I'm doing the in-memory computings, and also I focus on the monitor circuits, like to see the critical paths. And we also have a small group, like for the energy harvesting, is a PMU group for the power semiconductors, and the last but not least is the EDA group, is the electrical design automation. They focus on the methodology development, like the reliability analysis, the non-Gaussian timing, also the magic corner and the sign off. Like they are the simulator guy and focus on the leap. Okay, so the outline of the second part. So I thanks for my thanks for the 5 minutes of the introduction. So the second part will be the emerging non-volatile memories. So I will focus on the state of the art. And why the emerging memory is very important. Like we have the emerging memories like the MRAM, like the RRAM, like the FERAM, like also the FEFET-based SRAM, because the power dissipation is a main concern in Moore's law and also in the Moore. And we can see from the left figure, we have 3 different modes, the mode 1, mode 2, mode 3. So mode 1 is sleep. We can understand as the deep sleep. So imagine that we have the Apple Watch. So if we want it the battery to work as long as you want, so you need to put it in the deep sleep mode. So normally it's actual low power consumption. So the mode 2 is wake up. Like we have the Apple Watch, and I want to see the time. So I hand my watch, and I see the time. And so you need to wake up your watch, and it's going into the low power mode. And the mode 3 is a computing. What is a computing? Is that for the watch, it needs to monitor your blood pressure, for example. So it will take the huge computation during very short period and make decision to tell you about the results of the monitor. So in both mode 1 and mode 2, we call it low power consumption because it's cost 30 picowatts, or maybe mode 2, the 300 nanowatts. But for the mode 3, it's a huge power because the computing cost like the milliamps of the current. And for the watch, the Apple Watch application, normally we would like to it works as the sleep mode and the wake up mode. But for it's very few, like the few times of the runs, like it's in the active mode, because the active mode is not welcome in the IoT devices. But let's see the right button figure. So for the long time idle shutdown, like for the Apple Watch, so we need to back up energy and restore energy, even if when we use SRAM, DRAM, you need the power supply to guarantee the data storage. And for the DRAM, you need to refresh your data. So it's kind of the long time idle and shut down. But for the emerging memory, it can help us to do what? To do the put it in the normally off, but instant on. So instant on means if I want to use my IoT devices, I can run it as soon as I can and as low power as I can. So that is the emerging memory. The first benefication is it offers the zero leakage in the standby scenario. Okay, so the second importance of the emerging memories is that nowadays we have the huge memory, like the embedded memory, like the standalone memories with fast write, with a low supply voltage, and also with a high density. So for the non-volatile logic for normally off circuits and systems, we want to put our devices and circuits and systems as normally off. So we need to button cells, we need solar powers, and it's at a low end because it's a kind of the power constraint. That's we focus on. And imagine that we have the many interest applications like the deep learning, like the AI applications. So we want to do the energy efficient, like either the storage is energy efficient, but also the computing is efficient. So the in-memory computing is also enables the deep learning and the AI applications. So that's also the emerging memories that makes it important. So we can see the bottom figures that we have many interesting the applications like the IoT edge devices and the deep learning and AI edge devices. So they enable the usage of the in-memory computing and also the emerging memories. Okay, so the importance of the emerging memory, like even we developed the SRAM and DRAM. So SRAM is in the 5 nanometer and 7 nanometer. So we also have the innovation of the standard unit and the caches. So we want to do what? To do the emerging memory replacement. Okay, let's see the memory hierarchical. So we have the memory core, we have the CPU, and from the left to the right, we have the L1 cache, L2 cache, L3 cache, and last layer cache. And we also have the main working memory as a DRAM, and we have the secondary storage like the flash, like disk, and we also have the external memories as well. So from the left to the right, we have the speed, like we have the slower and slower, and we have the CPU cycles like the larger and larger, and the memory capacity is larger and larger. But our emerging memory can use to replace the L1, L2, and L3 caches, also the last layer caches. So we want to do this kind of replacement because we can achieve the zero leakage, we can achieve the computing memory, and we finally want to achieve the non-von Neumann architecture, like to put the computing into the memory, like we want to move the CPU into the memory. Okay, so it works well. I don't know. I don't know if you can hear me because of internet. It's okay.
It's okay, yes. But your slides are not anymore. Can you share your slides again?
Okay. I can I continue? Okay.
Yes, we can.
Yes, Hao. We heard everything you said,
Okay.
but your slides went off. So try to share your screen again. And
Okay. I'm going back. Okay. So that's the third importance of the emerging memories. Okay, so typical emerging memories include the recessive RAM is RAM, and the phase change RAM, and also the MRAM. The MRAM is for the magnetic random access memories. According to the Philip Wang, Professor Philip Wang, in the Nature Nanotechnology in 1916, in the 2016, so they announced that the MRAM, you can see the left figure, the green one. So it achieves 1 picojoule of about the right energy, and also the right time is 1 nanosecond. It seems that it's very optimistic for this kind of design. And compared to the other memories, when we compare to the RAM, the PC RAM, so and also the something like the FDSRI, that's very emerging memories. So we compare the density, the read speed, write energy efficiency, read energy efficiency, as well as the endurance. We can see that the very fast read speed and very good read energy efficiency, and also a very high endurance, like the 10 power 15 of the endurance. And although it's right speed and right energy efficiency is not good, but we can overcome it because we can just to take advantage of the read part of this kind of the memory, like the most of the kind of the scenario is like we do the memory read, but very few writing operations. So the bottleneck of the MRAM still will be the writing and the cost, because we can see that the tape out is very expensive for the MRAM, and also the process. The process is not as stable as we imagine that, and also the efficiency is not very good. Okay, so about this kind of the MRAM, it's used what? It's used as spintronic devices. And we can see that electron does not have only a charge, but also a spin. It is possible to construct a practical electronic devices that operates on the spin of the electron in addition to its charge. So it's announced by Professor Furtz and Professor Grunberg in 1987. So they found a phenomenon like the giant magnetoresistance. In short, it's GMR, and published in the Physical Review Letter in the 1988. And finally, 20 years later, they got the Nobel Prize in Physics in the 2007. Because of this kind of the phenomenon, and we finally to put this to switch this phenomenon to the MRAM design. So the first generation is a toggle MRAM, and after is a TAS MRAM. TAS is a kind of the thermal assist switching, and the third generation is STT-MRAM. That's the spin transfer torque MRAM. And the next generation will be the spin orbit torque MRAM and the VCMA MRAM. The VCMA is for the voltage controlled magnetic anisotropy MRAM. So among the different MRAMs, I think the STT MRAM is with the foundry establishment, because both TSMC and GlobalFoundries offers the opportunity to us to design the STT-MRAM, and you can use the macro, and even we make a very good deal, you can design the own macro by yourself. Okay, so about this kind of the foundry announced MRAM informations, the key feature will be the first is a versatile embedded MRAM. So for GlobalFoundries, they use the FDSRI, the fully depleted silicon insulator. And they announced that it achieves the energy efficient, the fast write enables the OTA update, the fast system wake up, and no static leakage through the MRAM bit cell. And finally, they can put it fully integrated with their 22 the technology as the last generation. I think the last generation of the platform of the of the process, and it's ideal for the IoT storage and computing applications. So this shows the In-MRAM bit cells, and you can see it's very simple. We have the word line to enable, and we have the bit line and source line, and to can have the current to switch the green part, the MTG, that is the magnetic tunnel junction. And we have the free layer, the fixed layer, and the tunnels in the junctions. Not only the global foundries, but also the TSMC, the first foundry, the first founder of the world, and they announced you can use the 22 nanometer and 28 nanometer technology to design the CMOS part, and also you can use their bit cells to put it as a macro and to design for the specific things. Okay, so the fabrication for the last 10 years about the MRAM. I think like the 16, maybe 18 years ago, for the ICC or maybe JSSC, they already published the papers and made the presentations on the MRAM. So they mainly focus on the STT-MRAM, the spin transfer torque, using the perpendicular magnetic tunnel junction with STT switching. Is with a kind of the industry recognitions, and normally they put it at the highest the metal layer. So we can see the right figure. We have the metal 1, metal 2, metal 3, and from the metal 3 we connect to the bit line, and up to the bit line we put the MTG at the highest the metal gate. And we can see the STT-MRAM development status from the 2009. So the NEC, Toshiba, Qualcomm, the SK Hynix, Micron, and even the Everspin, Infineon, and also some academic part like the National Tsinghua University in Taiwan. They developed several different kind of the MRAM. The future is very different. Their future is very different. So normally the difference in the bit cell, maybe the 1T1M bit cell, 2T2M, the 42M. The T means the transistor to control the bit cell, and the M is the junction in one bit cell. So we can see the right down figure is the chip size versus the cell size. So you can see that in the ICC, the 17, the SK Hynix, they developed a MRAM micro that uses a bit cell. It's very almost the same, the chip size, and I mean the density, and also the same size with what? With the DRAM. So that means for MRAM, if their performance is very good, and they have the opportunity to replace the DRAM. So for the SRAM, it also works because when the SRAM is scaling down to the like the below 10 nanometers, so we have what? We have a very bad SRAM density. But for the MRAM, the density will be the improvement. Okay, so for the MRAM industry participations, let's see the Everspin, the Qualcomm with TMC, and the Fujitsu, TDK, Toshiba, the SK Hynix, and they are all the players in the MRAM industry participations. So we can like the code for we can use a code for tape out, like maybe like the shuttles, like the MPWs, and to join this kind of the work. Okay, so for the emerging NAMs and especially for the MRAMs, I show the state of the art. So for the in-memory computing, it's the third part of my presentation. So why in-memory computing matters? Because the physical structure for data storing require area, like the area consumption. So we have the large capacity of the storage. So we need a very large chip area. So more data require cost for accessing. So the issue is the access energy versus the computation energy. because when we want to compute the data in the processor, we need to first to fetch the data and to put it into the processor, and after I finished, I need to write it back. So it's kind of the computation and also the access energy. And the traditional, the von Neumann architecture is we have the outside SSD and to the DRAM, to the SRAM, and finally to the PE unit. But you can see the long path cost very very high the movement as the energy. And the memory access and data movement dominate in nowadays workload. So nowadays workload, like we have the AI system, we have the IoT system, we can accessing the computer result over many bits if we use in-memory computing. So the in-memory computing, the major advantage is to amortize the cost of the accessing from memory, and also to reduce the amount of the intermediate data and reduce the transmission between data at different the memory hierarchy levels. So the third one is it can enable the parallel computing. So the in-memory computing is aims to slow the energy efficiency problem. And the state of the art of the computing in memories, that is the energy efficiency is their target. So we can see the right, the up figure. In the last the tape out of the NTHU, the National Tsinghua University in Taiwan, it achieved the 120 TOPS per watt about the efficiency. And recently I read a paper, they already achieved the 30,000 of the TOPS per watt of the efficiency. So high efficiency is high energy efficiency is their target, but the great higher and the critical specification is more and more. And we have the 50 energy consumptions in the random access memories. Normally we have two approach to achieve the computing memory. The one is to modify the memory, to do the work inside the macro. And the second is to do the 3D stacked. And in this work, we only focus on the modified memory, like we do the circuit design, circuit system design inside the macro. So the computation in memory, like the CRM, is with the challenge of the full custom interaction design, and the recent prototype reviews potential. Like we can see the from the 2016, and we have the different the SRAM. The up case is for the SRAM, and the downstairs case is for the RAM. So the difference of kind of the computing memory silicon development shows that the energy efficiency can be exactly improved by this kind of optimizations. But until now, we don't have the design of the MRAM. Even the MRAM computing memory is announced by the National Tsinghua University in 2020, the ICC, but it's only the near memory computing. I will show I will explain the paper in my later slide. And last but not least of the state of the art of the computing memory, it's like the multi-levels design. So we need a device guy, we need circuit sensitive guy, and we need the algorithm guy, also the architecture guy. So it's like the architecture, circuit, device, and the co-design about intent to improve the energy efficiency. Okay, so let's see 4 different kinds of the in-memory computing silicon work. So the first one is by the Tohoku University from Japan. They announced a logic in memory in 2016, and it's a JSSC paper it's in 2015. So it's kind of the magnetic tunnel junction based logic in memory hardware accelerators, and they announced as the world's first fabrication example of the non-volatile logic in memories. So what kind of logic in memory? We can see the schematic in the right side. So they can achieve for other operation using the logics the logic is put like the between the bit cells and the sensing amplifiers. So it's a simple the pass transistor logic. So the up case achieves the sum operations, and the downstairs case achieves the carry operations. So it's very simple. You can find it in the book. So it's a pass transistor logic, but we use it to design 8-bit non-volatile for other. And finally, they have the PE units and designed with the 90 nanometers MTG as the most process. So it's their 4-chip design and achieve a very good the importance is they are the first the silicon-based work about the in-memory computing, but only it's a logic in memory, and they do not to provide the very complex the operations. The second one is by the company. It's by the G-Fragon, and it's from American. So they use the in-memory computing as a 20 nanometer. I think it's the IP from the company, and the design a 40 megabits MRAM, achieve the 9.9 TOPS per watt energy efficiency, provide the multiple mode within single chip for mobile and IoT device applications. So it's the first co-designed processing in memory as the convolution neural network accelerators. So we can see the chip in the print board. The MRAM is just in the middle of the chip, and it's a kind of the accelerator with a host processor. So what they achieve this, like they use the CNN in a matrix form, and with each element consisting of MRAM, and they use the large sized models could be possibly loaded into the CNN chip, and they perform the 3x3 the convolution, and on the two dimension image at the pixel location using input from input buffer and the filter coefficient from the co-designed on-chip MRAM memory. Okay, so it's the second work from company. And the third work is from last year. It's from the IMEC and the KU Leuven, and it's the first STT-MRAM. So you can notice that it's analog computing. So analog in-memory computing, in short, is AIMC, avoids costly memory fetch from external memory as the normal advantage of the in-memory computing, but it's more energy efficiency than the digital mark. So they have the experiment like the STT-MRAM. STT is the spin orbital MRAM to implement it as a ternary weight for interface for the inference accelerator running quantized the DNNs. So the decoupled read and write path allows the IMTG with a mega ohms level. So note it's a mega ohms level, but for the STT-MRAM, it's in the kilo ohms level. So for the mega ohms level, it's very welcome because it can enlarge the R on and R off by turning the internal barrier thickness. And they also include the DTCO. It's very useful because it's a design technology co-optimization, and they put the analysis is to guide the process optimization. And so this paper shows the first analog in-memory computing, but it's using the STT-MRAM. It's not the foundry-based, but from the lab-based, it's okay for the design. And the last but not least, the fourth work is from the National Tsinghua University. I just mentioned about the near memory computing unit. It combines the output latches in the current-based sensing amplifier and the slave latch as an MCU, as a kind of the digital flip-flop. All NMCUs construct as a flip-flops chain in one bank for shift and the rotate operation. So they put their digital circuit. They use the NMC to replace the digital circuit to achieve the shift and the rotate operation. And also they use 22 nanometers and design the 1 megabit and use 1T1M, the MRAM macro, and to achieve this kind of the in-memory computing. But they confirm it's a near memory, not inside memory computing. Okay, so the other works. So we have many the in-MRAM computing related works, and other works are all simulation based. Like for the sensing based, we have very famous peanut tube from the UC Santa Barbara, and they achieved the in memory the Boolean logic, and to do some computing. And also based on the Boolean logic, we have the reference here, and also we have the writing based the work here. So until now, we see we mentioned the 4 different silicon work and a lot of the simulation based work about in MRAM computing. So the challenge, I at least five different challenges. So first is very few silicon work. I just list the 4 different silicon work. If you have more interesting work, please show me the link, and we can read together. And the second one is the mainly focus on the bitwise logic operations, and also the shift and also the rotate operations, very simple. And the third thing is it's hard to perform analog computing in the STT-MRAM because only the STT-MRAM is the foundry supported kind of the MRAM. And the fourth is the high writing voltage about MRAM. It also shows very limited endurance, the reliability issues of the device and the circuit. And finally, for the memory design, our digital CASS cannot follow exactly, because for the memory design, it's exactly the analog design flow. So these challenges make the MRAM computing is not it's not as faster as we can develop to replace the something like the interesting domains. Okay, so from this slide, I will show my previous work and our work, our ongoing work. So the first work of my previous work is MTG, is a magnetic tunnel junction based approximate computing by the reconfigurations. So we did the VDD scaling in the hybrid, the most MTG logic, and the key contribution is that we found that the MRAM is not stable, is unreliable. So we put it's like the approximate memories. So this kind of the things is we can change the two mode. We can switch between different modes, like the approximate mode and the accurate mode. So we use the joint strategies to improve the NV circuits, the sensing performance, considering the dynamic power, the leakage, the variability tolerance, and the sensing failure probability. So the circuit level design for the approximate computation is proposed, and for the magnetic tunnel junctions and the hybrid circuits. So it's my 5 years ago, the work of my 5 years ago. And our previous work, and second one is writing only in MRAM computing for the actual low power scenario. So we developed several methodology like the read, verify writes, and the self-write termination circuits. And our target is to control the yield, and we want to improve the reading yield and writing yield. And we perform the XOR in memory based on the pressure control, the writing mode, and the calculation speed can be improved to the 0.6 nanoseconds. And finally, an approximate calculation method based on the inadequate MTG write current is posed to reduce the power consumption. So this is like the NanoArc work like 2 years ago. So the work in progress is our in-memory computing about the silicon work. And we perform the binary or ternary storage the design with the modified bit cells. So normally we have the 1T1M. We can see the 1 access transistor and 1 MTG, but we add an additional controlled transistor to put it at the 2T1M, or maybe use the self reference So it's a 42M architecture. So the contribution is a single-step convolution. So we can perform the single-step convolution by the row decoder executes the multiple word lines to input parallel, and we can output through the pass 1 and pass 2 for the result on convolution and the bit counting about the fully connected layer. And we execute our design in the MNIST and also in the CIFAR-10. And we found that if the TMR, the internal magnetic ratio, is greater than 2 with the 40 nanometer MTG, or TMR is greater than the 1.5 with MTG smaller than the 35 nanometers. So the accuracy could achieve the more than 90%, 95%. And but this kind of single step convolution can achieve the 51.2% compared with that of the row by row with a slight decrease in accuracy. So the chip is in the, we just sent it to the fabrications, and I think it will be back in the December in this year. And the second interesting work is we try to achieve the analog computing in STT-MRAM. So we proposed a 62M bit cell and used the latch to make the equivalent TMR larger to realize the analog operations. And we find that integral current mirrors with feedback structure can effectively reduce the nonlinear degree of calculation. So different of the digital computing, the analog computing is like they rely on the current. We can see the left. We can put two current together and to based on the basic the Kirchhoff the functions and to realize the analog computing. But very simple, the ADC, the analog to digital converter, is required in the output because we need to transfer this kind of data or maybe to convert this data from the analog signal to the digital signal. And we're using the bit line to perform the analog sum of the product operation as well as the vector, the matrix, the multiply. And the result is that the equivalent, the TMR, can be improved to the 20 times. And the integral nonlinearity, the INL, is reduced by the 69.2%. Okay, so the first part is a highlight of the EnergyAware Spintronics. So I will mention 3 different levels. So first, the device levels and the interplay switching of the MRAM bit cells. And we use not only the SOT, not only STT, but only we rely on the SOT to put the interplay and the SOT first and STT second. So the 2 different currents, SOT switching current and the STT switching current, are sequentially applied to the device in the toggle-like manner. So the model is rely on Wilson's fabrication in the Nature Electronics in 2019, and we developed a circuit and to use their models, use their device, and to achieve the in-memory computing. And the second work is we rely on the VCMA plus STT. The VCMA is a voltage-controlled magnetic anisotropy. So this kind of the STT-assisted precision of voltage-controlled magnetic anisotropy can greatly reduce the supply voltage and the power consumption as well. Okay, so from the circuit level, we like 3 years ago, we start the MRAM on FDSRI work. The FDSRI is a fully depleted silicon insulator design strategy. So it's very famous with the body bias generator and also the flip-aware methods. So we use the ST microelectronics, the IP is a BBG IP, that is a body bias generator. So and it can provide a boost to our the bit line, or maybe to provide the boost to the word line to enable the voltage control of our bit cell. So this kind of the programmable body bias generator with a step size of the 100 millivolts is used to generate this kind of pulse and the forward body bias voltage. And it's very useful in the MRAM on FDSRI design. So we can see the group boundary have a several work on the MRAM on FDSRI. Okay, so for the system level, we started the speculative strategy about the design for the MRAM. So conventional common writing timing with the weak bit cell as unnecessary the power consumption. And we propose to use a speculative scheme, and it can use weak bit cells to monitor the writing operation as the process voltage temperature tracking writing time circuits. So finally, we designed the mixed precision MRAM and to put it in the image signal processing, and just for a case study. So it's also the continued work from our approximate computing, and we start it's like the speculative strategy about the MRAM. So the EnergyAware Spintronics about our recent work is MRAM macro building blocks optimization. Although the computing is very important, but for the memory itself, it's a storage. So we need to use the storage functions, like we need to optimize the power constraints designed about the row column decoder, the driver, the timing circuits, the sensing amplifier, and the reference, the current source circuits, and also the I/O circuits. And we use a hybrid simulation using the Verilog AMTG models and SPICE netlist to follow the analog design flow. And we can see that the feedback reference of the 1T1 and BTL, it's very useful because it can guarantee the high density and the approach, and the results can approach the 2T2 MTG yield. And also we can see the high sensing margin and the yield about, and we designed the SE, it can operate as low as 1.5 volt about the VDD. And here we publish this work has been submitted to the TCAS1, and we developed the new the voltage sensing amplifier, and to make both the sensing margin improvement and the sensing yield improvement, especially focus on the low VDD. Okay, the second of our recent work about the EnergyAware Spintronics is the self-timed voltage mode sensing scheme. It's use the sensing scheme that is can dynamically track the VBL, the bitline voltage string. And another work is the MTG-based loop replica bitline timing circuit. And we first propose the device circuit interaction for the process voltage temperature robot sensing for the and we published in last year TCAS2. And also we have aging temperature monitor circuits like BEAST. It's a kind of self-activated BEAST by aging temperature monitoring scheme. And the work is also the new memory access schemes, the device circuit interaction as the DTCO, the CMOS MTG dimension scaling, and the domain-specific system applications. Okay, the third very interesting work is the sparse realization in the unreliable MRAM. So the MRAM sparse realization is firstly proposed for the CNN, for the convolution neural network. It's kind of circuit algorithm joined implementation, including the MRAM, the locate, the patch, the CNN pre-training and retraining, and fine-tuning the steps. And we use the training retraining of the CNN and to alleviate the MRAM sensing failure. For example, the low TMR, the insufficient sensing voltage current, they cause the very low sensing the failure, and all of them can be alleviated by our sparse realization in the unreliable MRAM. So we finally to verify our CNN in the CFA 10. So the MRAM sensing can be speed up to use this kind of sparse realization by the 6.4 speed up and within the almost 85% of the capacity. So it's our last this year's work, and we published in the Transmag. Another very interesting work in this the high system level is we used to use the ENRAM macro we designed to replace the MCU, the building blocks. So for the MCU building blocks, we have the flash, we have the SRAM have the retention SRAM, and we also have the working memory as SRAM in the MCU. So the EMRAM replacements can we can replace eFlash, and the normally off of the always on the building block. So we can put the EMRAM to replace the SRAM. It's kind of a retention SRAM. So we tape out a 55 nanometers MCU platform, and we are now doing the MRAM replacement in always on regions, and like it's the first the work is to replace SRAM, because we found to replace, if we want to replace the flash, and we need to design a large capacity of the MRAM. But for this kind of SRAM, it's like the kilobyte. Okay, so now I'm going to the outlines about the conclusion and the perspective. So it's a very interesting work to presentation online. It's a research work during the pandemic. So we normally in China, we do the online group meetings and the deadline setup for the students, for our colleagues, and we participate in the virtual conference like the ICC and the ISCA, and we also writing the funding proposals from the NSFC, and the highlight of this work is the MRAM. So why the MRAM and low power matters? Because I think the MRAM itself is for the low, is very suitable for the low power scenario, and for the in-memory computing, the energy efficiency is our design target. So the third things I want to discuss is the importance of the foundry participations. Like we cannot join the integrated device manufacturing like the IDM mode, like UVSpin, but we can join the university shuttle, and also to participate the MPW with TSMC, with the GlobalFoundries, to participate this kind of the tape out work. And we also in my department, we also published one paper in the Nature Materials about the coronavirus pushed education online. So it's a very interesting work, and welcome to see the paper, and maybe we can find more interesting research points, and to how to perform the research work in the pandemic. Okay, the next perspective is emerging memory is a new device that must be EDA compatible, because until now we are fully the analog design flow for the MRAM. So we would like to have the digital flow like the SRAM design, but I think the DARPA American, they called this kind of the analog design flow, the analog design automations. So we need to follow this kind of the work, and hopefully in the next 5 or maybe 10 years we can achieve to design these kind of the emerging devices with very good EDA tools. And the conclusion of my work is that MRAM could be the next generation working memory, and to replace eFlash and the L3 and the last layer cache. And now the major stubborn issues including the cost, the reliability, and the density. And the second is the application specified usage is important. It's not for, we cannot fully replace the eFlash or the SRAM, but we can put it like the hybrid, the memory integrations. The third thing is the multi-level interaction design. as the DTCO is important for the MRAM development. So foundry in the industry can boost the research work from the academic side. And last but not least, is the in-memory computing is still under development, and I speak it from the 0 to the 1. And we have the logic compatible VDD, the good variability issues, and high density. And it will make sense if robust device, for example, the high TMR of MTG and the large capacity integration are possible. Okay, that's all of my presentation. And can you hear me? Okay, Rafaela, could you please you close your mic?
Yes, my mic's mute. Sorry.
Okay.
So thank you, Hao Cai, for your presentation. A lot of topics covered. So let me see if I can unravel that and add some questions from the audience as well.
Okay.
So first of all, in terms of the pandemic, as you mentioned, what about the research work that depends on lab experiments and things like that? So are you back on track now, or are you still waiting for when it's safe to come back to the lab and do the experimentation?
Yes, it's a very interesting question. So so the key point is that we don't have the collaborations with the world, and also with my own group, because normally we work at home, and normally we design for example, last night I run the DRC, but my colleague used the different DRC versions, and we make a lot of the errors. So it's not normal. It could not be happened if we worked in the lab. So I think it's the point. It's the problem. But at home, I think it's more like you can do as anything as you want, and maybe it's another kind of you can have some new ideas at home, even compare with in the lab. Okay.
Yeah, I find myself working twice as much, I guess.
Okay.
And I think I
Really?
think everyone does, especially in this kind of
Okay.
when you work with research or
Yeah.
something like that. When you have to be creative, I guess you invest all your time in being at home, and mixing your personal time with your work time is kind of messy.
Yes.
Yeah.
Exactly.
Now, heading to the more technical questions. So we had one question from Rafael Cardoso from UFS. So he said, first, analog IMC is amazing. And then he asked, when comparing the highly optimized processing architectures we have nowadays, IMC still looks more expensive and hard to achieve. Do you believe that this situation will change? What would be the main factor for this change to happen?
Okay, so for the in-memory computing, I think for the SRAM, for the in-SRAM computing, if how our target is 100%. So for the in-SRAM computing, it's already in the 60 or maybe 80%, because the SRAM, if we scaling the SRAM down to the 10 nanometer, or maybe we use the 5 or 7 nanometer to design SRAM, but the classical 6 transistor based we call it 60 SRAM is not high density. So it's already I think the result is 400 F square, about this kind of the density. But for MRAM, you can have the 10. For RRAM, you can have the 50 of the F square. So the F equals to your minimum transistor dimension. technical node. It's for the SRAM. So I think for SRAM, it's very definite. But for the emerging memory, for the ARAM and for the FERAM, I think it's already in the 20%, or I mean, it's in the 20 or maybe 30, because for the ARAM, you can achieve the bio-inspired computing. You can achieve the very interesting the stochastic computing, and also you can have the brain-like design follow the ARAM. We can see a lot of paper from the Nature and from the Science. But for MRAM, because until now, exactly, I think maybe there's no very definite work about MRAM. So I mentioned that MRAM still from the 0 to the 1, the step. So I'm trying to put it from 0 to 1, but I don't know my chip, the tape-out chip, when coming back. Okay, maybe it's a break. It's normal. But it was to try for the MRAM because it's still under development. But for all of the in-memory computing, either the analog way or maybe the digital way, and I think the scenario, the IoT scenario, or maybe your AI applications, it's already driving us to move straightforward about the in-memory computing. Okay.
Yeah, in my own experience, I designed some chips using 19 nanometer technology and then 28 nanometer technology combined with the MTJs, But the problem is that the lower you get in terms of CMOS, the better the process is, the harder is to generate the switching current, that is required to switch the MTJs, because this switching current is not going down as fast as we want to.
Yes.
So
yes.
Could you update us on that? Because I don't have access to the same technology as you do. So
yes.
What do you think?
So normally in the 28 nanometers, we have the 50 microamps to switch from the parallel to the anti-parallel. And if we can, so it's a key design issues, because we not switch the only 1-bit cell. If we want to switch 32 or maybe 64 bit cell together, so it's the milliamps of the switching current. It's very huge for the I/O, and it's so for the MRAM design, also for the in-memory computing design, I think the power management is also a big issue for this kind of design.
Yeah. So as you said, we have a lot to work to do in terms of the commercial EDA tools. So are you working on any, not only you and not only your group, but the group that surrounds you, are you working on EDA tools to make MRAM synthesis more automated and more?
Yes. So as I mentioned, we have a very good reference like the Pinatubo, published in 2016, the Design Automation Conference by Professor Xie Yuan. And he puts this kind of tool, like the online tool. We can use the Pinatubo, the tool, to generate the array of your any resistive arrays. But I have compared the results with the silicon-based results. It's not very equivalent. But I think why MRAM and why SRAM and DRAM is very popular and very easy for the designer to achieve, because we have a very good tools and it's supported by the foundry, at least. So foundry guys can give you this the memory compiler, and you can run it. And I think in Everspin or maybe in TSMC, they are ongoing developing such a kind of the tools, and to make it available very soon, I think.
Okay. Yeah. So I myself am invested on research for EDA tools for MRAM specifically. So that's come closer to my subject. That's why I asked.
Okay.
So
Okay.
Fernando Silveira said, "Thank you for the very nice presentation." And he asks, "You mentioned work on FDSRI by ST. In this process, is there a way to include the MTJ element that is already, established? How do you handle it? Or if not, how do you cope with that?"
Okay. Okay. Thanks, Fernando. And a long time no see. Okay. So for the ST, because we are using the FDSOI provided by GlobalFoundry. So GlobalFoundry, they provide the macro to us. Like until now, we can use IOs as a macro, but we cannot to design the inside the macro. Like we cannot to design the SA, design the arrays, but we can use it. So for the MRAM on FDSOI, we can use the macro. So when we have the macro, we can use the macro replacement in our MCU. So I have mentioned we have the MCU, the microcontrol unit work. So we have the SRAM. We can use the ST. We can use the GlobalFoundry's micro to replace SRAM, to replace the flash, and that's our recent work. It's kind of the architecture work, not very circuit design.
Yeah, in the past, I had we had the wafer fabricated in one foundry, and then they shipped this to another foundry to post process and add the MTJ on top of it. But it was very unreliable. So I think that it's better to see that the foundries are welcoming the process into their own establishment.
Even when the capacity of the memory is very large, so we can do a very good the lab work like in the 4K byte, but for 4 megabytes the memory is not good to change foundry from another foundry, or maybe to have the CMOS part from foundry and to move it back to the lab. So it's not it cannot be achieved.
Yeah, sure. Ricardo Hayes asked, considering reliability and tolerance to radiation effects, how you compare MRAM to SRAM?
Okay, it's a very good question. So for the MRAM, it's announced as it's an intrinsic the radiation immunity. It can achieve this kind of radiation immunity, but normally the radiation can affect the CMOS part as well. So normally we put so we have experiments in the radiation immunity related work. So we have the lib, the design lib about the logic, about the other circuits, and to achieve the radiation inside that part, but to keep the MTJ. So that is it's an up layer of the metal. So then we generate the case together, and that can have to have the very good reliability, because for MRAM it's announced can be used in the satellite, in the aircraft, and I think MRAM is better than SRAM, even in the I mean the 10 nano and 7 nano. The 7 nanometer of the SRAM technology is not very good for the radiation effect.
Okay, yeah, I think so too. I think that maybe we have to harden the CMOS part, invest on that, because otherwise it's going to be the weak point, right? Altamira Suzino, which is a professor here in FRGS, asked, aside of technology that are welcome to lower power of large VLSI circuits, we may wonder how much power does data traffic consume, for example, to access huge databases or high-speed streams. So I think his concern, even though you showed figures relating to speed, his concern and power, he's concerned about the data that the power that there has been lost in transferring data from one side to another. So,
yes. Okay, for the MRAM, the operation frequency is not very fast, and during our test results show that we have the maximum is 40 mega of the megahertz for the maximum, and it cannot run very fast because the limited writing the very long writing period. So I think for this point of view, we can selectively to slow down our to reduce our supply voltage and to put it as the low power part. So for MRAM, I don't think it's not suitable for high performance applications, but only for low power. For the ultra low power, it's very suitable.
We saw the emergence of phase change memory now in mass storage devices, such as the Intel Optane or other NVM devices that replaces our hard drives or even in data centers. So, do you think that MRAM will reach this stage of development in the future, or it's going to be more of a niche memory for certain applications?
Not yet, because the MRAM is very expensive until now for the tape out. It's really very high expensive than the normally the process. Even this year we try to launch a 14 nanometer the MRAM, but finally the cost it's very huge. Because for the PCM, the most the benefits is the low cost, but for MRAM, I think the problem is that the foundry cannot receive a lot of the MRAM how to say? I mean, not a lot of people. There is not a lot of people to buy MRAM. Like from the company, they do not have something to like the requirement. So even for MPW, this kind of the behavior is very expensive. So I think if the MRAM the process is more stable and we can call something like the 4 wafer and for the 4 wafer, because like 3 years ago it's even expensive than now, but now until now it's I can accept this kind of the price, so it's okay. So that means the cost is going down, and I think it can be last for next maybe 5 or 10 years. So the price will be the same with the normal the MPW. So that will be welcomed by the university, by the industry, by the companies, I think.
Maybe through research, we'll reach the scale that we need to make MRAM more cost effective, right?
Yes.
Yeah. Speaking of MPW, so we got an interesting question here from Hamid Mahmoudi. So he said, hello, thank you for the talk. And he asks, which foundry do you use for MRAM fabrication? How to get access to MRAM foundry for university research?
Okay, thanks, Hamid. So it's a university shuttle. So I need to keep the shuttle as a how to say it cannot be announced in the internet. I'm sorry.
Yeah, that's the answer I was expecting, but I think that we see that countries and governments are establishing MPWs around the world. So we have initiatives such as the one from the University of Minnesota with their C-Spin Center. I guess Tohoku University has a spin research center. In China, you have plenty as well. So we can see that in France, the MPW provided by CMP was supporting MRAM development. So I think that we can see that there are several initiatives around the universities, right?
Yes.
Okay, so I guess this covered all questions. So I would like to thank you, Hao, again for being with us and being with us so late at night. But
it's very pleasure to share my idea.
So you will be available on YouTube again for those who missed or wants to see your presentation once again.
Okay.
And so I'll hand to Ricardo to do the final announcements and finish the session. So thank you, and hope to see you in Brazil in person some other time.
Yeah, sure.
Yeah. So Ricardo, thank you again to Rafael to chair the session, and thank you, Hao Cai, to do this talk, very interesting talk today in a very exciting subject. Thank you very much to do this talk late night in Nanjing. So, and I hope to see you face to face in the near future. I also would like to motivate you and all the attendees to prepare also papers to LASCAS 2022 that we hope that will be a face-to-face edition in first week of March in Chile. So it's also a nice opportunity to have a good paper in a nice conference in a nice location. So this can be also a nice excuse for you to visit us in south of South America. So by the way, from Chile to Porto Alegre is in regular times is just one direct flight, so very short one. Thank you very much, and see you next Friday.
Bye-bye. Thank you.